Next, we have Dale. Dale is a developer at Workday. He has been doing everything from designing hardware, yes, to JVM internals. And now he says he's doing Scala only to get paid. His dream is Swift, is UIKit, which is functional on Swift. Let's see if that dream will come true. All right.
OK. Right, so this is live coding-ish, which is to say I was alive and I wrote code, and now we're in Xcode. And we're going to see if we can demo some stuff. I'm going to fly through these slides pretty quickly because I made too many of them. And also, I presume that there'll be a lot of repeat information for people who have some sort of basis in functional programming and immutability with Swift, but hopefully we'll show something new for everyone. So we're going to start by making some simple stateful classes. So I'm going to create a class called the time, which is just a simple wrapper around NSDate. And despite the fact that it's mutable, it still needs an initializer. You can't actually just leave the thing be null like you could in Java. So that can be a little bit confusing at first. So then we have another class, which is called watch, which is just going to it's going to be a simple wrapper around a time object that also needs an initializer. So then we're going to try and actually do something with these classes. So we're just going to exercise them with a very simple test, where we just create a constant, which is now. We create a time object. We instantiate a watch with that time object, and we just assert that the current time is equal to now, which obviously that's not really testing anything interesting, but it does get us to show that the code is running and we can build things and test them. So once that's there, you'll see that the test is called giving a tourist the time. So what happens next is a tourist asks us for the time. And the reason being he's about to get on a flight back home, and there's a 5-hour time difference. So he goes and sets his time to be our time minus 5 hours. So we then have a test to verify that that got set correctly. And if we see that, that test passes. Again, it's pretty straightforward. And where it gets surprising is the next part. Well, not surprising, but annoying, which is we add one final assertion, because no good deed goes unpunished, which is we then go and check our own watch again. And what's upsetting and confusing is that having now done a good deed and told a stranger the time, our watch is now wrong because of shared mutable state. So the assertion here is basically saying, no, now is not actually equal to 5 hours ago. Things are wrong. So the reason for that is that with a class, when you give the time, you give the time. The person you've given the time object to now has a reference to that time object, and they can mutate it. Because, as you can see here, the value is a var. And so how can we fix that? Well, one of the options is to make it a struct instead of a class. And so I'm just going to swap out the class keyword for a struct keyword and see what that does. And does it compile? Does the test pass? Turns out the answer to both of these is yes. So with that one simple change, we now have the test passing. So this basically, when you see the word struct, it gives you a lot of assurances about how you can reason about the code. You no longer have to worry about spooky action at a distance from someone who might happen to have a reference to the thing that you're working on. And that just leaves you free to reason more locally about the code that you're actually operating on. So with that in place, we're going to see what else we can get rid of in terms of mutability. So we can get rid of vars, hopefully. So the first thing I'm going to do is replace that value and the time with a let. But what happens then is we get a compilation error, because the way that we were initializing the watch relied on mutability. So one of the things you need to learn to do when using immutable data structures is you can't just partially initialize them and then ad hoc go and patch them by mutating them afterwards. You have to have all of the information at creation time in order to initialize an object, which may sound like a lot of overhead and difficulty, but what it means is that whenever you have an immutable value type, you can trust it. It's completely initialized, it's completely correct. So what we go ahead and do there is we'll delete the mutating instantiation, and we'll go ahead and put in an immutable time and watch, and I think that should then fix our compilation errors. And the test should run. Cool, they do. So we can also get rid of the var in the watch, and watch can be made a struct. And that doesn't actually have any effect on this current test. It just shows that like a lot of the time structs are compatible with classes, unless you need the specific details of classes like identity. Okay. So also it turns out that structs have default initializers. So all of this boilerplate that we had there, we don't need anymore. So we can get rid of that. And we now have much more concise code, which does exactly the same thing. So are we still on value types? I hope so. If not, you can talk to me later. But for the rest of the talk, I'll just be giving more examples of value types. I won't be really trying to justify their usage. So one good thing to know is that arrays are value types. This is quite unusual in Swift, in things like Java, in things like C, C++. These have pointers and they have identity, and you can't change one without changing the other. But here you can see that we start out with our array. We make a copy of it. If this was an array with identity, that would just be a reference pointed into the same array. But here, when we update the array, verify that it's true, turns out that the second array still has the original value 1 in there. Just run the test just to verify it. So that's quite unusual, is that these collections are value types. But again, in fact, like in the early days of Swift, just how value typed arrays was kind of different. If you took like slices and whatnot, they could be mutated strangely. But now it's just, no, they're value types, that's it. Move on. So similarly, dictionaries are also value types. You can see a similar sort of a test there. Alrighty. So we'll come back to dictionaries later, but for now we'll be mostly looking at array manipulation, which is a very common imperative style of thing to be doing. And so we have some new lessons to learn. So we're going to start by defining a simple struct that we can put into the array. So this is an XY coordinate. And we're going to define a function called rightmost, which allows us to get the rightmost coordinate spatially in the array. And we're going to implement that very imperatively. So as you can see here, we've got a mutable variable, which we assign to be the first element in the list. Then we iterate over the list, and if we find a better match, we just replace that result because it's mutable, and then we return it at the end. So very imperative. We're all very used to writing code like this. So then we'll just add a very simple test for this. Now, you'll see that there is a compilation error in that test, and the reason for that is that we can't call assert equal with coordinates. And the reason for that is that, strangely enough, and I don't understand this decision, structs aren't equatable by default in Swift. You have to explicitly make them equatable, which isn't a hard thing to do. We just define that they conform to the equatable protocol, define the function, and we're done. And now the test should run and pass. And it does, so that's good. So can we do anything more to our tests to make them a little bit more thorough? Like, what happens if we test an empty list? Any guesses? I think we can probably see things are going to go wrong, because array indexing isn't safe. It's what Bill Venners refers to as a YOLO method. So when we run that, actually, I didn't actually run that, so I should run that and crash it. So we run the test, and we crash. So let's just reset that. OK. So now we're going to do what any imperative programmer does when they hit an edge condition, which is they add a big ugly if. And so now we'll return nil if the thing is empty. And you can also see that now the return type is an optional, where it wasn't previously. And so now the test should pass. But also, our test is pretty stupid. It doesn't actually do anything. So we should put an actual assertion in there to make sure it's testing something. And that does actually work. OK, so let's take our imperative implementation, and let's try and make that a little bit more functional. So what we're doing here is we're going to use reduce. Now, reduce is one of the first things that people tend to quite like when they start working on collections in functional programming, because it's a lot like just having a mutable variable that just kind of gets handily passed around to you every time. And so what we do here is it's the same sort of thing. We pass in the first element, and then the body of the reduce is similar, where we say if we find a better option, return that, otherwise return what we originally had. So that's cool, but it's still ugly. We've still got this conditional here. So is there anything that we can do to make that better? And we can. We can call sort on the list and then simply return the first element. So we pass in a closure which allows us to sort. So that means we can sort on the x coordinate, and also means we can sort big to small rather than small to big. So we can completely control that. Then when we return first, that itself returns an option so that we don't need to worry about that. Now, there's probably someone somewhere thinking, yes, but this now runs in O of n log n instead of O of n, which is true. But how big is your n realistically? So I would tend to say, when you're looking at something and say, oh, this is readable, but this is probably faster, profile it. Don't make it faster until you need to. Worry about the times of humans, not the times of computers, unless they're both measured in seconds. So, onto another data structure. So this is just an enum, which represent days of the week. And we're going to serialize that out to an int, which we do by bit packing. Again, very imperative. This should be very, very similar to what we had before. The only reason I want to show this, and I'm just going to fly through it a little because a lot of it should be familiar by now, is like I said, we often use reduce, and reduce is good if you have a collection of things and you want to return a thing. But if you want to return a collection rather than just a single thing, often reduce is confusing or overkill. So what we're doing here is we have a collection of raw values of days, which we then filter, which produces a potentially smaller collection of raw value of days, which we then map, which produces a new collection of equal length but of different type. So if you're trying to return a collection, don't go with reduce unless you've thought about it really long and hard and you reckon it's definitely the way to go. So, all right, I said back to dictionaries, and this is the last part, because dictionaries in Swift I think are a bit weird. So here we have Roman numerals and we have clock numerals. I don't know if people know about clock numerals, but a lot of time if you look at a Roman numeral clock, the number 4 is actually represented by 4 i's, not IV. Partially it's for visual symmetry because the 8 on the opposite side is so wide. Partly it's actually a cost-saving thing. I can explain that some other time. So we're trying to replace the number 4, but we have to make clock mutable. And that's not cool, because then we're making it mutable for this, but what's to stop people mutating it elsewhere? So we need to get a bit clever here. We need to get a bit creative. So we're defining an extension on dictionary. Extensions in Swift are pretty cool. Scala tries to do something similar by using implicit conversions, which are a lot more magical. I like the fact that these aren't magic. And you're probably saying, oh, but you've got a var right there. What the hell are you talking about? And I do. But you'll see that update value is actually a completely pure function. Even though it's implemented using a mutable variable, there's no shared mutable state there. That mutable variable is completely constrained to that function, and no one outside of it will ever see it or know that it's there. Now, as you can see, we get a compilation error down here because this method signature already exists in the library, and we're only differing by return type. And it turns out that if we make var no longer be mutable, if we make clock no longer be mutable, that actually resolves the ambiguity in the overloading, because the other method is a mutating method and this one isn't, and therefore it can puzzle it out. And so now our tests all pass, and we have no local mutability, which is nice, which just makes maps a little bit more like other things to deal with. So the very, very final thing on maps is filtering, which is another similarly common kind of thing. So here we have another mutable way of doing things, and by now we've seen a whole bunch of different ways of getting rid of that mutability. So we're doing it here with an inline function, which does a whole bunch of manipulation to allow us to ultimately use reduce here. But that's kind of ugly, and it's kind of non-generic. So what we end up doing is we create another extension, which is filter. You can see that this combined method in filter is probably about as hairy as the previous method was, but it's also generic and reusable. So we can now replace the body in our original code to use that, and we see that it gets a lot nicer. We have this closure, which defines our filter. The key is a don't care term. We look at the value, is it an even number of characters, return it. So We take all of our hairiness and we push it out into extension. That becomes library code. Once you've written it once and tested it thoroughly, you forget about it forever. And now dictionaries are a lot more useful. So, thank you. Questions? Oh God, what is it, Brian?
Just on the array thing, how you said that everything in the array is a reference. So if I define the class and I put it into an array and I duplicate the array, and then I read the class back from the second array, does that mean the class is no longer like?
So if you have an array of classes, that's an array of references. So when you make the new array, that will still be an array of the same references. And so, yeah, you'll still be able to mutate the same class. Yeah. Yeah.
What are you using to do that?
I'm using this, which is Scala.
Did you make it?
Yes.
Put it up on GitHub.
I will eventually once I've cleaned it up. Yeah.
The old tale that would never get published now.
Anything else? No? You want to know what a struct is that, Brian? Yeah? Okay. Thank you.